All right. Back to there. All right, we were here, random variable probability distribution. Okay, random variable, again, is a numerical value determined by chance for an outcome of a procedure. Rolling die, you have the variable could be one of the numbers that are rolling. Probability distribution, a lot of times we're going to use a table or a histogram. Sometimes we're going to talk about a formula. So fill that up. Okay. All right. So in the preview, we talked about discrete and continuous random variables. A discrete random variable, either a finite number of values or a countable number of values, where countable means the fact that there might be infinitely many values, but that they represent a result from a counting process. So discrete is countable, meaning you can go from one to the next one. That's what I mean. Typically, most of our situations are going to be a finite number, meaning that there's 6 of them or 25 outcomes or something. It's a finite number. But it could also mean an infinite number that but they're countable in that you can go from one to the next to the next. A continuous random variable, the difference is it has infinitely many values, and those values can be associated with measurements on a continuous scale without gaps or interruptions. Okay? Discrete is like jumping from number 1 to number 2, then to number 3, then to number 4. Continuous, I'm not jumping from one to the next. I've got all of those numbers in between are part of the thing too. All of those numbers all the way. It's continuous. It doesn't stop. No gaps or interruptions. Discrete is one to the next to the next. Continuous, there's no gaps in the variable. Discrete, one to the next. Continuous, there's no gaps. Continuous. Measurement of people's height. Continuous variable. How many people are in a room? Is that continuous or discrete? Discrete because it's a count, right? That's a good way to maybe try to look for those things. All right. Requirements for a probability distribution. These 3 things. These are important things. There's a numerical random variable x that its values are associated with a probability. Okay, so a numerical random value or variable that has value and is associated with probability. Okay, so the number of girls that are born out of 2 births, that's a numerical value, and we can figure the probability of that. Sum of all those probabilities must add up to be 1. Why? Yeah, it's one situation, and all the probabilities should add up to be 100%, which is 1. Okay, so the large sigma there is summation of the probabilities should add up to be 1. Okay. The third one is that each probability is between 0 and 1. Of all the ones that are going to be in our probability distribution, all of them have to be between 0 and 1. There should not be any negative probabilities or probabilities that are greater than 100%. Don't exist. Those 3 things are requirements for probability distributions. We'll talk about a few things. All right. What does that graph look like? A histogram. Not a normal distribution, but it's a histogram. That's the idea of what I'm after here. It looks like a histogram. It is a histogram. The only difference in a probability distribution and a frequency distribution or a histogram that we did back in chapter 2 is that the y-axis is going to be probabilities instead of counts. Probabilities instead of counts. Probability histogram, similar to the relative frequency histogram that we did in chapter 2, but the vertical scale is probability, not counts. That's the difference. There's not much difference. Looks the same. Got to be careful on our scale. Make sure when you're looking at charts, if it doesn't have probabilities on the left, like small numbers that are between 0 and 1, then you're probably not looking at it's not a probability. You are not looking at a probability histogram. It's got numbers that are bigger than 1. You're looking probably at a frequency histogram, not a probability histogram. So probability histogram looks just like frequency histogram except for the y-axis. Y-axis is probabilities, not counts. All right, here's some formulas that we'll talk about with the mean, variance, standard deviation of a probability distribution. All of those things are values that we found before, mean, variance, and standard deviation. We're just dealing with it in terms of probability this time instead of just a number, okay? So the mean, what's that letter at the beginning there? I don't remember what that's called. Mu. Mu is the mean. It's the sum of all the x's times their probability. Okay. Sum of all the x's times their probability. The variance is the sum of the difference between the variable value and mu squared times the probability. And here's a little shortcut method to the variance. Takes several decimal places before they change for their different values. So this gets us close to that. It's a little cleaner calculation. The summation is just the sum of the squares times the probability for the values, and then minus mu squared. And then standard deviation. Remember, standard deviation is just the square root of the variance. When we were doing that with regular data back in chapters 2 and 3, the calculator would find the standard deviation for us, and when we wanted the variance, we just squared that number, get that. So if you've got the variance, you can take the square root of that, and it'll give you the standard deviation. Let me look at ways of doing this. Always talk down here. Mean, variance, and standard deviation of a probability distribution. Expected value. This is an important one. It's big. It's pretty important. Expected value of a discrete random variable is denoted with the capital E. So see capital E in one of your problems that you're working on. They're talking about expected value. Expected value represents the mean value of the outcomes. It is the mean value of the outcomes. Expected value and mean value of the outcomes. Same. Go back to the previous page. Same formula for mu. As expected value. Exact same formula. They are the same thing. Mu and expected value of the discrete random variable are the same thing. Mu and capital E. Same things. Expected value, I guess is a more common term. If you just say mu, that doesn't mean a lot to anybody that's not in the statistics side of